I'm Ian Graves. I'm from Intel, and this talk is a bit of a dovetail on what Vladimir just presented. So Vladimir did a lot of work with CodeSnippets, and we at Intel are working on an API that's going to be more user-facing, developer-facing in Java, called the Vector API. It's pretty exciting work. It's a lot of interesting stuff to play with. I kind of feel like, you know, a 16-year-old driver that just got behind the wheel of a car and then crashed it into a mailbox or something, because that's what happens with these kinds of projects. But it's very enjoyable, and the work is very rewarding. So I'm excited to describe it to you today. So not to be outdone by the legal disclaimers seen previously, I have a couple slides of disclaimers. I'm not making you any promises. This work is very much prototype. Your trademarks are your own, et cetera, and so forth. If you'd like to go back and read these, I'm sure they'll be somewhere on the internet. And then as a more concise disclaimer, the code in this presentation is, like you've heard before, prototypical, subject to change. It lives in Project Panama, and I'm also told to say that it is licensed under the GPL v2, class pass exception. You all know this, but here it is. So if you're interested in the code, you can get it from the Panama repository. It's online, waiting for you to check it out. So just a quick overview of this talk. We're going to go through a quick introduction, give a brief foray into CodeSnippets as I've been using them, then discuss the Vector API and its design and some of the challenges and opportunities therein, and then I'll do a quick wrap-up. So this is primarily right now a collaboration between Oracle and Intel, the Vector API is, though we're open to anybody who wants to participate. So you've probably recognized some of the names here, the familiar suspects, some very nice and very intelligent people, along with myself, working on the Vector API project. So we're always looking for more people to add to this list. So briefly, terminology, since the word vector is highly overloaded here, API is overloaded, CodeSnippets, et cetera. CodeSnippets is what Vladimir is working on, encoding instructions in Java, hosted in Java, executed in the JVM runtime, and then being bound therein with method handles for invocation. The Vector API is a layer over that, a veneer over that, that provides some additional safety, type checks, and regularity to the underlying layers. Since the ultimate goal of this API is to be cross-platform, it needs to be sufficiently removed from a particular architecture, but still straddle that line where it doesn't impose an additional performance penalty in so doing. So it's implemented on top of CodeSnippets, and the challenge of our work so far has been to make sure it doesn't come at a significant cost. So there's a number of explorations that we're sort of engaged in right now to investigate what's usable and what is feasible. So our motivation, many popular applications benefit from data parallel computation. Everybody probably has one they can name. Off the top of my head, we see a lot of libraries for machine learning dependent upon data parallelism, or they would benefit from data parallelism. Currently in the JVM, architectural support for data parallel architecture extensions is opaque. So this kind of parallelism occurs in the form of superword optimizations, loop unrolling, and that's subject to a bit of brittleness, right? You have to write your code in a way that optimization passes can come in, recognize them, and optimize them, which these optimization passes enjoy a lot of success in the wild, but there are algorithms that are particularly resistant to optimization passes, making good hay with them, especially when a developer, a human, can write them from the get-go in a vectorized form and see the results almost instantly. So we're looking to expose pure Java solutions in this area. To avoid JNI interfacing, a lot of solutions now that would link to something like libbloss deal with a JNI overhead. It's not the same as, say, inlining these instructions into your program, per se. So developers are left with this choice where you have to make sure that the data that you are operating over in a parallel fashion is sufficiently large that the overhead of the JNI is not overcoming your calls out. And then secondly, we want to make sure that these solutions minimize cruft and boilerplate in the generated code. So we want to make sure it's good quality. So like I was just saying, we want to expose those things. Portability and performance, we want both. Trade-offs are ultimately necessary in some cases, but we'll cross those bridges when we get to them. And scalability, as Vladimir and I actually have a very similar slide. I dumped it when I saw him do it, but you all saw the Intel Intrinsics website where you type in, the name of an instruction, and then there's, so many different operations and instructions for you to choose from. And that's just one AVX, or that's AVXs for x86, but that's just one vectorization extension. So we're dealing with sort of a combinational explosion as architectural extensions grow, and then multiply that by the number of different architectures we want to support. We need an approach that will scale for implementers, that we can keep our minds wrapped around it and not have to hopefully cut down on the implementation complexity. Vectorization is a very rich and powerful tool that comes in architectures, and it is deep. So when you're dealing with vector instructions, it's easy to get lost in some of the details, and when you try to abstract over those details, you can end up making some of your programming models very unidiomatic and very confusing and strange to use. Likewise, you can over-normalize these things and end up looking like C, making it very un-Java. So the goal also is to have idiomatic APIs for developers to use and understand for vectorization. So code snippets. So we're treating code snippets, like I said, as a substrate for our implementation. Brief review. Code snippets are a portable API for expressing primitives. In our case, they're more flexible to prototype and to experiment with than implementing hotspot intrinsics, which usually involves a number of different pieces of work. Going forward with things like Graal on the horizon, encoding these things in Java have certain benefits as far as technical debt is concerned. We don't need to necessarily carry that forward. If we do a lot more work in hotspot and then Graal comes down the line a few years later, we don't have to do this all over again. So having it in Java is a very nice thing. And then ISAs can use the same API. So everybody gets a crack at it. It's in prototype phase, as we've heard, but we've observed some pretty good performance characteristics, though we're not quite to the point of benchmarking everything. You'll have to wait until Java 1 for that. But we have observed good code quality and good performance on small examples, but we need some bigger examples to really definitively describe the nature of our performance. So method handle invocations combined with code snippets is a really good approach for inlining code quality, et cetera. So just from my angle, implementing a primitive, like we said, we bind to method handles. The method handles library has additional combinators we can use, since whereas before in regular Java, you just write plain old Java, arithmetic expressions, et cetera, you can't, invoking things in tandem with each other, or method handles that have data dependencies. You can also use method handle combinators for those, and that's really handy. And then, like we said, we use method type to describe the types. Vectors represented by the long objects. In the best case, the wrappers can be elided, the values can be registerized, but escape analysis and box elision is still work in progress, but it's looking very promising at this time. So Vladimir mentioned that there isn't an assembler in Java, but we're working on it for x86. We've got some of the pieces coming together. It's more of a macro-style encoding system right now, but it's looking good so far, and you can check it out on Panama. So implementing a machine instruction, in this case, this is VADPS. So instead of integers, we're looking at floats. We have our type. We have our feature checking predicate. So in this case, VADPS requires AVX. So check the CPU ID flag, is AVX present? If it's not, bomb out with an exception. If it is, keep going. Register masks. So in this case, VADPS is a 3-operand thing. It needs a result register to store in and then 2 operating registers. It's a non-destructive-y flavored operation. We get these via JVMCI. And then down here is some macroized x86 encoding that I probably will avoid going into depth, aside from saying it's VEX encoding. There are a number of methods to help support that. If you're really interested in that kind of thing, you can check it out on the code base. But we will probably encapsulate this a little bit more, but this is what it looks like right now. And so we end up emitting the bytes of the VEX encoded instruction that supports VADPS in this case. Similar to Vladimir's, we have a checked invocation point. So with the addition of a pure Java equivalent function for sanity checking, it's just good practice. Then we wrap VADPS in sort of a checked invocation point. If something fails, an exception, we raise an error. Otherwise, we just continue. We use this as the public accessing point for this method handle, but it looks just like your run-of-the-mill method. So a small example using this kind of thing is we're interested in adding arrays. And this is just what you're looking at right here is just an iteration over some arrays, a left and right array with a destination array to sync the results into. For brevity's sake, or for lack of complexity's sake, we assume that the arrays are mod 8 in length because we're not going to do a whole lot of cleanup right now. This is just for short demonstration's sake. And then we iterate over the arrays, adding the left and right results and then storing them in res, which we do in the next slide. So add arrays, just to isolate this code, for in the next slide you'll see why. But we have a method handle for loading from a float array, loading a long 4, so a 256-bit register gets loaded from that. We add the two together, and in this case, we are a sysc instruction set. So if you got it, use it. So patchable vecutils.vadps is doing a sunk load right out of memory to save us some time and some instructions on the back end. And then, so we do that operation, store it in RR, and then we dump it back out to the float array. So that's our scaled load and our scaled store and our addition. To generate the code, we provide lots of flags. In this case, we disable enrolling in superword as a comparison to baseline operations just to see that we're getting some gains. For tiny examples like just array addition, the superword optimization will wake up and make total hay out of that. And even if you generate the best code, your code will probably be about as good as superwords for this tiny example. So you won't see any gains unless you turn superword off. So we turn it off just to make sure we're actually seeing some real gains over a simple scalar operation. So let's see, hopefully that's a little readable. Okay, so the code it generates, and this, just trust me on this, I had to crop it just right so it would fit on the slide, but this is the entire body of add arrays dumped out. So snippets are pointed to with minimal anything else. And then you see at the bottom, we do some cleanup, and then we return. So snippets used in this particular way, I know in the previous talk we observed boxing issues, but snippets used in this programming style where you render a long 4 from an array, use it in an intermediate fashion like so, where you have a dependent chain of operations, and then sync it back out to an array, results in minimal spilling. You see how the loads occur, the first 2 operations. At the very top, you have vMoveDQU, and then you have VADPS with 1 operand coming from memory. And then there's a vMoveDQ back to memory where we write it back out. So there's no saving going on because these are value-ish classes. And they don't need to live anywhere. We're not uttering their names anywhere outside of this body. So C2 is able to discharge any spills. It's a pretty nice trick. So this will be probably one of the only remarks I make on performance. Disabling superword and loop unrolling, we see about a 40% reduction in clock cycles spent in that kernel. So we're counting on clock cycles in this case. Wall clock time, there's still some overhead occurring from other places in the library, and we're in the process of chasing them down. But on a fine-grained level, on a perf level, where we're particularly interested, the loop kernel itself is quick. So we're working on bigger and more intensive workloads to sort of stress this, but so far it looks pretty good for a prototype. So moving on to the vector API. It's like I was saying, ISA extensions to support vectorization are very expressive. You'll have the same operation supporting numerous different kinds of operands, XMM, YMM, ZMM in the case of the latest AVX 512 that's coming down the pipe. So this creates sort of a headache for people wishing to abstract over this. There's sort of an n cross m problem that occurs if you want to parameterize by types, et cetera, sizes. So it's a challenge just to wrap it up. But we need it anyway if we want to have a platform-independent abstraction for the vectorization. So it needs to capture all this in the spirit of Java itself. So platform independence, once again, I keep saying this. Along with meaningful static checking, we can live in the land of method handles all day, but we have a type system, so we might as well use it statically where we can, where it makes sense. And where it doesn't make sense, we can always defer to runtime, but the more static checking, the better, as long as it doesn't come as a significant cognitive load to users. And you need to use familiar patterns. So the vector API, as it is right now, was proposed by John. You can check out the initial draft proposal on the Panama Project listserv, but the base type is this notion of vector, unrelated to long4, that's parameterized by an element type and a shape type. While these types, the element type isn't particularly constrained, we're looking at the broadest support in float, integer, and double types. In the case of x86, the AVX extension resides mainly around those data types. There are operators for longer and shorter things, but the most complete set of operations live in those size types. So that's where we're spending most of our time. And so the draft implementations of the vector API are checked into Project Panama. Sort of a loose outline of the structure as it is right now. One of the things we're particularly interested in is rendering vectors from arrays. And vectors from boxed primitive array types, if we're parameterizing by generics, then that in our fields that we were to render from would be parameterized as well. It sort of behooves boxed types, boxed arrays, and so we get pathological results if we stick with boxed arrays of boxed primitives. So what we do is we do the specialization routine, running a similar play that we've seen in streams with IntStream and double stream. So here we do float vector, which is a subclass of vector itself. We hide some additional factory methods here for rendering in and out of primitive arrays, because that's where we really want to spend most of our time. And then hidden behind the scenes are the specialized float vectors, which support the specific code snippets for sized operations in 128, 256, and other sizes to come later. So the basic functionality, vector-vector operations, you see some of the familiar guys. just adds moles and arithmetic operations on vectors. You have vector A, you have vector B, you add them together, you return a result, which is a new vector, and it's immutable. That's the thinking right now. The long vector objects and the instruction set architectures that we work in are immutable-ish as well. So, if you're using a non-destructive vector operation, then it helps to stay immutable. And it's something that's nice. Immutability is a new, a newer feature, not a feature, but a new trend that's being championed everywhere. So we're starting from immutability and seeing how far this takes us. So some more advanced operations on vectors. You have scalar vector interfacing, so getting elements in and out of vectors, putting elements back into vectors, which it's not a set, it's a put. So slight nuance there, but put would mean we generate a new vector. And then we have horizontal reductions on vectors, which are a little trickier. Vladimir mentioned that some code snippets would be more than just one instruction, and horizontal reductions usually end up being more than one, especially where floating point is concerned, and you have a canonical horizontal evaluation for floating point. So we've had some light discussions as to how about the floating point fidelity of the vector API, and I think we're going to stay faithful to strict FP style evaluations. So we have to write it in a particular way. There are some horizontal operations for addition and other similar things in the ISA, but they don't evaluate in the way that you might expect. They reduce kind of like this instead of like this. So you reduce, and then you reduce again, kind of in a tree-like local fashion. So it's good for integers, less for floats, but it's a work in progress. And then loading and storing two arrays. These are the box forms, but they're there for reference. And then sort of the fully realized expressiveness of the API, and where I think some of the particularly interesting stuff resides. So you have maps. Maps takes a unary operator op and maps it over a vector, sort of tweaking every element in the vector. And then you have a masked version of that map. We have a similar map, or say, you could also call it maybe a zip or some kind of a reduce. You have two vectors, you have a binary operator, you reduce them down to one vector. Likewise, masked version of that. The masks and some of these other types, like shape, are also specified in the repository as well. But in this case, you can kind of expect their behavior. You can kind of predict their behavior. Mask just directing in a bitwise fashion how to execute lane-wise. So these are particularly interesting, and I want to stick on this, but I have one little note before I go there. So the previous kernel we specified with code snippets looks pretty similar in size and shape with the vector API. We just mask over it with some factory methods. We have some extra additional type safety. But I'll say right now that given the way that longs need to be boxed, that we're still working out this problem, the vector API in its sort of wrapped form sees a lot of artifacting of the long objects on the back end in the code generation process. So we are working on it, but we're also investigating alternatives that, I shouldn't say alternatives, but other approaches to complement the vector API, specifically approaches to deal with some of this fully realized expressiveness that we are really interested in being able to apply to vectors. So higher order components, right? This is something we really want. We got lambdas in Java now. We should be using them, right? But this comes with some interesting challenges. So in essence, this is like the loop customization problem. The programmer specifies a loop body, and the loop body is specified lane-wise. So if you have an element of float, element type in float, the user just wants to say, look, I have this lambda, it works on floats. Here's some arithmetic. Do whatever it is you gotta do to make this vectorized. It turns out that's like not the easiest thing to do. Because if you're given a lambda at runtime, and it's lane-wise, how do you know what's in it? I mean, anything can be in a lambda. A whole Turing tar pit can be in a lambda. So how do you vectorize that in a way that the user can easily say, well, I wrote this code and I expect it to be vectorized with these characteristics? Because we're in this area of perf, right? So people want to be able to write code that has pretty predictable characteristics. So what do we do here? Should we focus on introspection of lambdas just for this API? And I would argue probably not, because that would be asking for expression trees in Java, and that would be opening up a whole can of worms just to make this one feature here work. So I think there are other ways forward where we can enjoy a lot of this without so much pain. Basically by saying we need better control of what the user is able to say in a loop body. We can do this with factories for constructing the operations that we want to vectorize, but they need to be composable enough that people are willing to use them. So if we give the user just a library of bodies to map and say, well, this is the add body, this is the mul body, good luck. I mean, they just execute one, execute the other. You don't want to be that fixed, but you want to have enough composability where they can say, all right, I have all of these little components. How can I wire them together to form a new loop body that I need for my computation and still see the gains that I want to see? So instead of just regular higher order, full-blown, firing on all cylinders lambdas, what we can do is we can stay in that realm but focus on kernel construction in these bodies. We can provide components that people can use. We can make them composable. OK, sounds good. Constraining to what's vectorizable. Great. Some interesting constraints that help us in this area are that most vector operations are either unary or binary operations. So if you have an add, you have 2 arguments. If you have a not, you have 1 argument. And there are a few that take more. There are a few that have kind of immediate fields that you need to do a little bit of dispatch on. But overall, you're constrained into this little, slightly ragged, but arity2 and smaller type operations. So you can start from there. And we can continue using method handles to illustrate this whole thing. So just as a brief sketch of what I'm talking about. Say you have your method type, and then we instantiate some code snippets. And what our goal is to represent what's at the top. We can start with method handles, and then we can start combining them together with combinators. And then we can do some fan out. Yeah, that's a little bit of fan out. And we've basically constructed what's at the top. So we can do it with method handles. The combinators are there. We can start from a high-level lambda-ish representation and encode it in method handles. So there has to be some kind of transformation that exists to get us from a higher-level representation to this method handles representation. Because really, it's just combinators all the way down with code snippets at the leaves. Let's just open these up a little bit. So we want wrappers over this as well that have some static checks and some shielding from the brutality of the underlying architecture. One method is proposed by John. It's up in Panama. You can read it. It was an I think both methods here actually share quite a bit. You can read about it more there. I'm gonna skate around it a little bit in this presentation because I focused a little bit myself on a slightly different approach. But it is mapping vector operations and relating them to the operations that are arithmetically available in Java and in the bytecode. So it's a very tight-fitting correspondence to Java bytecode and operations that we supply to be composed in lambda bodies or higher order loop bodies. So another approach, and this is one I've been playing with, is to use a lightweight syntax tree. So not one like C# syntax trees, but just a little syntax tree that we can construct and then maybe apply some transformations to get us back down to method handles. So it's still very much in the work, yes, but some of the benefits still remain like they were in the Lambda version, which is we can think about it lane-wise. And once we think about things lane-wise, we have this benefit of where the runtime system can actually select which vector operations which wide vector operations are available in the particular operations that the user specifies. So the user doesn't have to constrain themselves to AVX2 or AVX1 or some other width-constrained extension. So some quick thoughts. So, right, most vector operations are expressions. Expressions are basically trees. Method handles can be combined together in a tree-like fashion using some of the usual suspects. So you can make things in a graph-like fashion and compose them together. That's really great. So permute arguments, collect arguments, filter return, and we're seeing even more being added into method handles. And I'm very glad I came to JVMLS, or else I wouldn't have heard about all the new stuff that's coming in 9 that is totally relevant to this work. So method handles have added benefits here. We've observed some good code, so why not? And coding this way, we've already seen, can help elide boxing. So this is sort of the idea. So if you construct an expression tree, it's just a tree. You have a visitor. The visitor traverses the tree. The visitor then produces a bound-up method handle composed of all the corresponding method handles that relate to this expression tree. So that's cool, but wait, there's more, right? Boom. So if you just have a different visitor for any kind of method handles you wish, so if you have the method handles in the back end present, you can query which visitors you have available. You can dispatch that visitor to traverse your tree, build your computation, and then execute the best computation that you have available on your system. So you can sort of divorce yourself from worrying about what's on the right and stay in the nice world on the left. So just as to illustrate this a little bit, so babies first, little EDSL, embedded domain-specific language for this. We have an expression interface. We have add mul knots, sort of building up a tree here. And then we have trace expression for debugging, and I'll elaborate more on why this is necessary in a second. We have ways to introduce constants. So in the case where you have constant values you want to load from, add to, start from, you do have to actually utter a long for make, and so you pack those with your constants lane-wise. That's fine. This only ever corresponds to the utterance of one make. So you have one long for on the heap, one long two on the heap. That's cool. And then you have your actual evaluator, which is a kind of reductive visitor in the sense that it traverses the tree and collapses it all down to one value, in this case being a bound-up method handle. So one thing to note is trace. What that is it's like a tap on the expression tree. When you compose method handles and you want to see the values flowing through this computation, trace will, if you have an expression tree, trace will break the connection between two dependencies and route a long for out where it realizes it. I say long for all the time. It could be any kind of long, but I'm sort of fixed with long for in my head. It routes a long object out, realizes it in the high-level Java sense as an object that you consider, does some inspection with it, hands it off to a consumer. The consumer prints it out or something or does some kind of debugging routine, and then passes the value back on through to the rest of the expression tree as though it wasn't there. So it's kind of a non-side affecting aside from your I/O inspection routines. So what this looks like is you have a binary operation, a classic binary operation, parameterized by this expression type, which is itself parameterized by the type of the constant leaf nodes. So you have an expression left, right, but instead of being a body that you execute directly, you're now using sort of a functional symbolic trick. So there's kind of a plumbing inversion that happens in this, where once you have composed your expression, an evaluator first plumbs this with symbol nodes with constant values to know whether or not they correspond to the left or right value. So these fall through your expression tree, which are symbolic in L and R. And you get a syntax tree out, and then it can traverse the tree. So some advantages of doing this with lambdas, because you could just do this with a constructor, but if you have lambdas that are predefined, you can actually compose the lambdas in the classic ways you see in the Java util function sense. So you have your and thens and your compose and all that. So you can compose these together and compose expressions in a lambda sense. So you retain that sense of composition, but it's still very symbolic. And I leave out the code for this, but once we have these, and I still have exper there, but that's expression float. Method handle binary reduction takes one of our operators that we've defined in this fashion, and then also takes source operands, so an array left and right, which are our sources, and then a syncing array, in the style we saw in add arrays before, but in a more generalized sense. So we do a binary reduction, left, right, dest, we give it our lambda body, and we can execute it. What this does is this binary reduction does a selection of who's my evaluator for the system I'm residing on. And in the draft implementation, it just assumes the presence of AVX2 and goes along its way, plums it, generates method handles, and then invokes the method handles in a fully applied sense. So what I was particularly interested in this experiment was to see how specialized we could get the code, like how shrunk down, specialized, no additional call, invoke overhead, et cetera, and so forth. So to do that, then you invoke it once just to say you invoke it, and then you do it like 25,000 times just to make sure that like everything's fully in line so we can get the next slide and brag about it. So this is the generated code from what started as an abstract syntax tree hosted in Java. We have the array base addresses here. We have our loads. And there's a lot of text here because a lot of this is debugging. So you have a little bit of cruft at the top, but it's not much. You move down, so the snippets are outlined in snippets. So a nice thing about CodeSnippets Vladimir has done is when you print the generated assembly, the snippets are wrapped so you can find what's actually a snippet and what's being generated by CodeGen. So snippets are encased in these little snippet locations. The names for them are listed as well. So we have our two loads. And then after our two loads comes our vectorized add and our vectorized mul. And we store it. And then another thing about the binary reduction I forgot to mention was that it uses looping method handles. So where's Michael at? He's over there. There you are. Method handle loops. You have a customer right here. So those are great. Those are great. So before that, I had to have these little, dangling static methods that I would have to bind to myself, but now I can use the API. That's great. So now I don't have all these mystery methods that never get invoked directly. They just method handle bound. But with loops, that's where we're going to go with this, the method handle loops. So essentially, this is a counted loop, except that it steps 8 instead of 1. So at the bottom, you see just the loop bookkeeping. So we compare to, I think hex 200,000 is the length of the array, just for test's sake. And then if we're there yet. If we're there, we fall out. If we are not, we jump back to 83B 2670, which is right where the first load occurs, 83B 2670. So the code that falls out of this is like very nice. There's the loop, there's the vectorized operations, and it feels really good. So if expression trees are so great, Ian, why don't we just use them all the time? Well, so there's some issues with the expression trees that make them probably not the one-size-fits-all answer. And the one that comes to mind for me the most is control flow. If you're reasoning about lane-wise operations and you want to begin branching based on one, but that one lives in a vector with another one that doesn't want to branch, you now have this kind of, oh gosh, what do I do? So you have to seed some, you have to make a choice. So the vector API, as stated earlier, gives you more high-level branching possibilities. That's not to say, though, that we could get some control flow mimicked in masked vector operations. So if you have ternary style sort of total arithmetic branching, so ifs in sort of the functional sense where it's if this or this, both return expressions, that's a possibility. You could probably do that with some masking or some very limited, well-understood control flow choices. But as far as masking operations are concerned, those are a little bit harder to come by in the ISA for like a total set of operations at this point. So TBD on that, working on it. So essentially you're kind of presented with this choice where you can have fine-grained control with coarse-grained data, or you can have coarse-grained data with fine-grained control. So control being control flow. You can make your choice. I would hazard to guess that the expression tree's high-level kind of loop body construction approach can get a lot of people a lot of mileage without having to delve into specific vector level reasoning about them in that way. So I think there's something for everybody in both of them, and the expression tree approach may end up living in the higher order components of the vector API, but like I said, it's all a prototype and it's all TBD. So the wrap up. So some challenges to idiomatic design here. The boxed elements, and I mean not the long objects, but generics behoove box fields. So how can we reduce our complexity of our API knowing that value types are coming? Well, we're kind of stuck until value types come, but that's okay. We can do a lot of hand specialization to get rid of our boxing. Immutability, in this case, is facilitated by new, which is fine so long as escape analysis can work on it. So if we can ramp up escape analysis and our coding styles so we can avoid unnecessary allocations, fine. But if something messes up, as I've seen in some tests, if you have tight loops and you're allocating long fours just go right under the garbage. Like they just get tossed right into garbage. You have to be really careful how you do it. And I think some of this behavior will play up through the vector API itself if users of that API aren't careful enough. So it has to be understood how to code in this API to avoid these things. And it kind of gets me into this place where I'm a little less comfortable, where you say vector operations return immutable objects, but no objects really get returned. It's just kind of this value thing. It's intermediate if you use it the right way. So you risk falling into this like operations and semantics twilight zone where like the semantics of the API are highly dependent on compiler optimizations working correctly. And it's not comfortable, but if Valhalla is coming, we can just kind of, continue on a little uncomfortable and then, we'll make it out of this phase. Lastly, idiomatic is a moving target in Java. I mean, I've demoed some of this syntax stuff before, and people kind of go, huh? And so I am loath to impose too much Lisp-like syntax, S expressions on people just to use vectorization. However, I think the code gen kind of speaks for itself, that methods in this vein have value. So how can we take this value and make it palatable to the developers who want to vectorize their data processing? Like I said before, value types are coming. They're not quite here yet, but we can play like they're coming soon. So yeah. So anyway, so continuing work, we're enhancing the baseline vector API, kind of finding that minimum viable API. Doing some more exploration on higher order functionality because I think that's a really rich and very powerful component to the API. And we're digging into what the trade-offs are. So what I showed you right in this last set of slides, or last set of images of code generation, was an incredibly specialized, data-specific, operation-specific set of code gen. So how can we back off of that and still get the code quality that we want and be flexible? What are the trade-offs? What do we got to do? So we will be reporting back at Java 1 with some hopefully better data and on perf and just code itself. And I'm looking forward to that. So if you're interested, Panama project, you know it, you love it, it's up there. Discussions are on Panama Dev. Vector API code is in that directory there. And the prototype implementation, as we said before, probably it'd be nice to have AVX2, so check your proc info. If you don't, you can probably still do quite a bit too. So just be warned, it's still a bit rough around the edges, but if you want to try it, it's there to play with. So that's it for me. So thank you.